Welcome everybody to the boot camp, the Sublinear Algorithms program. Let me start by introducing myself. My name is Sampath Kannan. I am practicing to be the associate director here starting in July, but I'm already serving in that role since January. For most of you are familiar with the Simons Institute, but for those who don't know, this place was founded in 2012 with a generous grant from the Simons Foundation, who continued to be the main source of support for the Institute. And we're looking good going for at least 10 more years. Then we will see about more money to generate and so on. But we have good support from the foundation for a long time. The Simons Institute, as you all know, is the preeminent center for theoretical computer science. There's none like it in the world, bringing people together for concentrated periods of time and really having collaborations generated and so on. It's got a great track record of producing successful collaborations. It also is a great training place for young researchers in theoretical computer science who go on to become leaders tomorrow. There's also a great history of interdisciplinary research at Simons. I mean, this is one of the places where we focus on the core, but when we talk about quantum computing or error correcting codes or something like that, we connect with other disciplines very strongly as well. One of the prides and joys of the Simons Institute is the collection of videos that we produce from all the talks that are held here. It's the greatest possible resource that one could have for theoretical computer science. And I think boot camps especially, no pressure on the speakers, boot camps especially are the pride and joy of the Simons because they are a great way to learn about any field. Okay, so look forward to this great boot camp. I want to thank the organizers of the whole program, the Sublinear Algorithms program. Renit is here, Artur, Piotr, let's see, Jelani, Asaf, and Noga are not here. Clement is there. Sorry, I didn't see for a second. Clement is here as well. That's right. So that's all the organizers. We got them all? Yeah, that's great. Want to thank them all. So a few logistic details, and I see people with their cups raised. And sorry to say that this place is food and drink free. So at the next available opportunity, please dispose of your food and drinks, or you can have coffee and food outside, but not in the auditorium. That's how we kept the chairs stain-free for so long. And then we have refreshments twice a day, but lunch is on your own. There are lots of great places on the south side, a few cafes right here at the business school and the law school, but I'm sure some local will guide you to something nearby. And in case you need to store your bags and valuables, there are lockers not too far from here, the day lockers that you can use as well. Anyway, have a great boot camp. Ready?
Thank you, Sampath. Thank you, Simons. And also, I want to thank Sandy Arani, who also helped with a lot of the arrangements over the last 2 years. So this has been like a big team effort of Simons and Carolyn and all sorts of people. So this was actually a lot of work, but we're very excited about it. The idea for this whole program is that locality of computation is sort of an issue that comes up in many types of computing, in sublinear time, in sublinear space, and also sample complexity in sublinear and sample complexity, in distributed, in massively parallel computation, and lots of other areas. So we hope that this program will highlight the sort of the interactions between the view of locality and how it impacts these other models of computation, and also some of the impacts that came out of this, of looking at things in this way. Okay, so it's a very exciting area. So this boot camp will give both classic results as well as some of the new advances that are emerging in this field. So it's a very exciting area. There's lots of new results and new directions that are happening. And so we hope to give you some sort of overview of what's going around. And we were told that this boot camp should be boring for experts. But hopefully it won't be boring anyway, because many times we're getting new views on old problems. And so I think that it actually should be interesting for everybody. We're starting out today is focusing on sublinear time algorithms. We'll look at sublinear time algorithms on graphs, functions, counting subgraphs, sampling algorithms. Tomorrow, we're moving on to the distributed massively parallel models and connections between those and sublinear time. There's many techniques that cross-cut and many techniques that don't, but we'll see a bunch of them. We'll have a number of talks on that. On Thursday, we'll have several talks on data streaming, including techniques such as core sets, new techniques in lower bounds, adversarially robust streaming. And Friday, we have sort of a mix of talks on distribution testing, including privacy, and how one could test distributions for assumptions for learning algorithms. And in the afternoon, we'll have talks on sketching in linear algebra and edit distance. So I think it's quite a varied set of topics, but there is a core theme, and we'd like to start with that. So our first talk is by Artur Czumaj, and it's an introduction to property testing, and it's going to focus on property testing for graphs.
Thank you very much for introduction from Sampath and then from Ronit. So as you heard, we are supposed to be giving you some boring talks. So apologies. It's on the other hand, as a speaker of the first talk, it's really a great excuse. If you'll be bored, it's not because of me. Just blame the organizers. Anyway, so what this talk should be about, So I want to tell you something about property testing, focusing on graph problems. It's introduction. Even though this introduction, I will kind of try to show you my personal view on these matters. So I will be just giving you some definitions, and then we'll be trying to tell you what are interesting models that people have been studying. I will be mentioning some results. There are many more results which I will be not mentioning because just lack of space. Okay. Okay, something is happening. So first of all, what is property testing? I do hope that all of you are familiar with this term, but in general, it's the task of distinguishing inputs which have some specific property from inputs which are far away from having this property. So I remember a long, long time ago when I have seen some talk of Ronit, she was introducing this on an American example. I will try to introduce this on a British example. So you have some fantastic castle, and you want to distinguish whether a given property building is a castle or it's some, ruins. So here we are not really thinking, okay, this cannot be a castle. We are saying it is far away from being a castle. So we are kind of not really interested in exact definition. What does it mean to be a castle or not? We're interested in kind of distinguishing something from something which is far away from that. So in general, the motivation here was that quite often in many scenarios, this is really a natural question to ask. So we are often interested in just, distinguishing something from something which is far away from that. So another example often is, for example, whether you want to see whether a given book is in English or is in some foreign language. And of course, we can usually easily do it without reading the entire book. So these are kind of things that we would like to distinguish here. Now, there are many other examples. So this is something which is very important, very useful in cases when the input data is changing all the time, and we don't really have time to check every time whether this is still satisfied exactly. And maybe actually in the context of this program, an important thing is that this can be often seen as some kind of a sanity check. So you are getting something, someone is giving you a book, and you just want to make sure that this is something like the right book or not. Okay, so this is kind of the main setup that people have been studying. In general, we have the word of computational complexity, where we have classical decision problem, So we're given some property, and we're given some input instance, and we want to check whether this input instance satisfies this property. Here we are interested in some relaxation. What are the benefits? So first of all, we do know that for many problems, this first decision version of the problem is just NP-hard, or we cannot resolve it. On the other hand, this setting of having the relaxation often allows us to come up with good solutions which are much faster, much better. So this is kind of the motivation behind that. Now, one definition that you should always think about is as follows. So you have some property at hand, then there is some input coming, and if input satisfy the property, that would like to accept it. Now, if the input is far away from satisfying the property, that would like to reject it. Now, as you see, this is this notion of epsilon far, and that's something which is very much problem dependent. So typically, this means that we want to modify at least an epsilon fraction of the input instance to obtain an object satisfying a given property. The next thing is we do allow some errors. So we are interested in randomized algorithms which allow to have some error, and would like to say the error is at least 1/3. It's kind of an arbitrary constant, smaller than half. One can always amplify that to much higher probability. Now, I will be talking about this epsilon far in details later, but one usually should think that epsilon is a small constant. So here we are saying it's, for example, 0.1 or 10% or 1%. We are happy to accept instances where even after modifying 1% of the input, we are still satisfying the property. But want to reject everything that you have to modify more. The focus of this talk is about graphs. And for graphs, we would like to kind of understanding what does it mean that a given property is far from being satisfied. So for example, the intuition is as follows. So you are looking at these two graphs, and would like to say both of them are essentially connected. Is one of them not connected? The first one, I mean the left one, is not. But they are kind of close to being connected. So we would be happy to accept these two graphs. On the other hand, if you have something like that, which is clearly far away from being connected, you would like to reject it. And then the idea is, how can we formalize this notion? So these are kind of standard problems that people have been trying to study. So these are standard properties. So we would like to know, for example, whether a given graph is planar or not, whether a given graph is k-colorable, or does it have a good clustering. So these are the properties that people have been studying, trying to understand how quickly can we test these properties for graphs. As before, all of these problems requires at least linear time, and many of them are NP-hard. However, in the setting of property testing, with some appropriate relaxation, we can obtain sublinear time algorithms, or often even constant time algorithms. So this is kind of an obvious game that we would like to exploit. So now I think the very first thing is really to understand what does it mean, what does it mean that we want to relax satisfying a property? What does it mean relax the notion of being good? Being not best, but good. It's kind of difficult notion in general. So for optimization problems, so for example, for a given graph, what is the maximum click size? We could say, okay, we can try to approximate the size. But for decision problems, it's something which is slightly more complicated. So how to say, okay, the graph is close to being 3-colorable. So let's just try to think about the definition that we are saying. So as before, our goal is to say, okay, given an input instance graph, given some property at hand, would like to accept a graph which satisfies this property. For example, it's 3-colorable. And would like to say, okay, if a graph is epsilon far from being 3-colorable, would like to reject it. Now, as I said before, this notion of epsilon far is relevant to the distance to the property, and we have to define this distance to the property here. So in general, we are saying we need to change at least an epsilon fraction of the input to obtain an object, a graph satisfying the property. Okay, so how we can do it? Before I'll go into that, let me actually mention also, so we have kind of two types of property testing algorithms. The definition which is given here is for two-sided error tester. So it can err both if the graph has property and if the graph is epsilon far from property. One can also actually consider also one-sided error, which is that we can err only in the second case. So this will be sometimes important in some cases. And one important reason is that one-sided error tester is typically giving us some certificate that the input graph does not satisfy the property. Okay, so the setting. So we would like to have the problem distinguishing between the case that graph G has a property and is far from it, and by far means we have to change at least epsilon fraction of its representation to obtain a graph with property P. And here are some first problems. What does it mean, an epsilon fraction of its representation? What does it mean, an epsilon fraction of graph representation, for many of you? Any thoughts, any suggestions? Especially for those who are not expert in property. Okay, so it does depend on the input graph representation. And this is something which we want to study here. So we have this proximity parameter epsilon, and we have input graph, and we would like to accept graph that satisfy the property and reject something which is epsilon far away, and we want to define the notion of epsilon far away. So it does depend on the input representation. The first input representation that people have been studying was the adjacency matrix. So you are given a graph represented by adjacency matrix, and you would like to say the graph is epsilon far away from having a property, being free colorable. If you have to modify more than epsilon fraction of the entries in this matrix to obtain a graph which is free colorable. What is an epsilon fraction? Essentially, we're saying you have to modify at least epsilon times n square edges of the graph G to obtain a graph satisfying the property. This is one representation. Now, people have been studying this case for graph with bounded degree. And then usually we're interested in having a graph where we are able to modify epsilon the n edges in order to obtain a graph satisfying the problem. The field has been really introduced in a sequence of papers. First, Rubinfeld and Sudan, they came up with some theoretical concept of property testing in general. And then Goldreich, Goldwasser-Ron, and Goldreich-Ron, they came up with the concept for graphs. So this is kind of the notion which has been introduced many years ago. And after many years, so this was 20 plus years ago, we know quite a lot about different models. And today I will try to talk about all the settings which are of interest here. So first of all, people have been studying the setting of adjacency matrix. And in this setting, we understand the model quite well. For example, as I will argue shortly, every hereditary property can be tested in constant number of rounds with constant query complexity. Then if we are given a graph, sparse graphs, where we are given an access to adjacency list, then some properties can be tested in constant time, some properties can be tested in sublinear time. We understand this model quite well, but not completely. The most natural model that people are studying for graph algorithms, you are given adjacency list representation. So some vertices may have very low degrees, some may have arbitrary degrees. We understand much less. This is something which we still don't really understand well. And then actually directed graphs. This is something which is a challenge. Okay. Any questions about this so far? Yes?
Sorry, what is a hereditary property?
I will describe this shortly. So this is kind of a generic, yes.
Just constant time means we consider.
Yes, okay. So I will be using the term constant time rather than constant sample or query complexity, just for simplicity. This means that constant time means we're querying the input graph in a constant number of queries to the input graph. So I will be using the notion of time, which is more or less just query complexity, how many times, how many queries to the input instance I'm asking.
So Artur, just a clarification. So when you say sparse, you really mean bounded degree, not just
no. So that's an informal description. So I'll be talking about this much more in more details later. But good question. And actually, so nowadays we have two great books about property testing, one by Oded Goldreich several years ago, and then more recently by Arnab and Yuichi. Is Yuichi here already? He's not. Arnab will be also here at some moment. So this is these are thick books talking about property testing, usually in general setting, but there are always several hundred pages about graph property testing. So property testing has been used in many different settings. So here my focus is on graphs. People have been studying this also for functions, for distributions, for many possible settings you can imagine.
Artur, maybe one more question on the basics. So do we know which things have polynomial complexity in the epsilon parameter? When you say everything is known, we know.
Oh, no. I never said everything. Did I?
No, maybe you didn't.
No.
You said you know quite a lot. Okay.
We know a lot.
He was careful in his imprecision.
Yes. I remember that a few years ago, I was giving some talk at some conference, and to make some dramatic introduction of something, I said that, this model, everything is known. And then someone, well-known person, stand up and was complaining. So all these models, there are still lots of exciting questions. The difference is, this model, I haven't defined this model exactly yet. This model, people have been studying for 20 plus years. We understand a lot. This model, bounded degree graphs, we understand quite well. Arbitrary graphs, little. Directed graphs, even less. Okay. So now I want to go into details about all the settings. So first model is adjacency matrix. So what we're saying is, graph is epsilon far from satisfying property if, in order to obtain a graph satisfying the property, we have to make at least epsilon fraction of these entries to be changed. And here's kind of the access to the oracle. So this is kind of the model. We are really studying the oracle model, where this matrix is given to us through the oracle. And we can ask, okay, is vertex I, so we're assuming that all the vertices are labeled from 1 to n. And we're just asking, are I and j connected? And this is kind of a single query. So when I'm saying that the complexity, the running time is constant, it means we're just making a constant number of such queries. I'll be using the notion, I'll be talking about time all the time rather than query complexity. Okay. So this means that in order to obtain a graph satisfying property, we have to modify at least epsilon n square edges, which means either to add them or to delete them. And in principle, you can say the matrix is symmetric, so maybe it's 2 epsilon n square, or maybe half epsilon n square. I don't care. To some extent, for simplicity, this is kind of our notion. If you think about it, it's something which is very suitable for dense graphs. For sparse graphs, if you are saying, I can change something for epsilon n square edges, that's something boring. Okay. So this is kind of the setting. So we want to accept every graph that satisfies given property. Would like to reject every graph that is epsilon far from given property. And if the graph is in between, we kind of can give arbitrary answer. And the complexity, which I will be using here, the running time, is number of queries to the adjacency matrix. And we can err with probability 1/3. And sometimes we want to actually have one-sided error algorithms, which means here we're always right. So let me actually start with the model. So suppose that my task is I want to test if a graph has a triangle. I'm saying this is a very easy example. What is the complexity of this task? Assuming n is large and epsilon small constant. I know that few of you know the answer, but I would like to hear this from those who don't know the answer, who are trying to figure out the answer. Why this is easy?
I'm going to answer, but now I won't, because that would mean I don't know the answer.
So what?
But 0.
What is 0?
The complexity.
I mean, yes. No. I mean, yeah. So you don't really have to check any entry because you can always accept it. Oh, sorry. You can always accept it, yes? Because if you are given any graph, you can take a triangle, so modify some like 3 edges in the graph, and you will have a triangle. Okay. Highly non-trivial example is test if a graph is triangle-free. And this is something which is much more complicated. Okay, so here, as I'm saying, complexity is 0. We can always accept such graphs. But for this problem, actually, complexity is much more complicated on one hand. On the other hand, it can be done in constant time. And so here's the notation. When I'm saying that something is done in constant time, this means I'm assuming that epsilon is a constant. And usually I would try to elaborate more about what is dependency on epsilon. But here I'm just saying it can be done in constant number of rounds. This number of rounds does depend on epsilon. And I'll give some more details later. And this is a trivial task. This is something which is highly non-trivial. I mean, nowadays it's maybe standard, but it's still non-trivial combinatorics. Now, there was a very nice tool introduced over 20 years ago by Goldratt and Trevisan, and sometimes also mentioned Alon among those. They actually noticed that if our goal is to just come up with constant time algorithms, we can consider only algorithms which are of this form. So what does it mean? Randomly sample some set of vertices, and then consider the graph induced by this set of vertices. Okay, so here's an example. So this is, okay, so all other algorithms will, almost any other algorithm will have at most quadratics, cannot have more than quadratic speed up. So what are we doing here? So this is our adjacency matrix. We're sampling some number of vertices. And then we're looking at the graph induced by these vertices. Okay, you may not see, but this is gray. That gray, that gray. So some entries are gray. It's whitish gray, but it's still gray. So in short, what we're saying is we're sampling some number of vertices, and then we're looking, oh, here it's maybe more gray. Okay, here I was confused myself. So we are sampling some number of vertices, and then we're looking at the graph induced by this vertex set. And then we're checking whether properties satisfy for this graph or not. Actually, the trick is sometimes it's slightly different property. But in general, this is really the setup. So what does it mean for us? That all algorithms that we are considering are very simple. Essentially, just sample some set of vertices. Yes?
Does the result say something about the size of the set you sample?
Oh.
So you have to know it.
Yeah, okay. So they are very fast property testers, which means often the size is very small. All algorithms are very simple. For example, and about the size you will see in a second, property testing for bipartiteness, for example, Want to check if graph is bipartite or not. What you are doing, sample randomly some set of vertices, look at the induced graph, is it bipartite or not? That's the whole algorithm. As your colleague is saying, the key question is, what is the size of U? And this recipe is saying nothing about it. It's just that all algorithms can be done in that way, which is simplifying algorithmic part a lot. Okay? And of course, the key question, what is the size of U? And many, many years ago, first there was some paper, in the original paper, Goldrake, Goldwasser, they showed that this is something like polynomial of 1 over epsilon. And then Alon and Krivelevich showed that actually it's O tilde of 1 over epsilon, which means that the complexity is of order O tilde of 1 over epsilon squared. So, I mean, if you are interested in algorithms, that's not the field for you. All algorithms are trivial. The analysis is really the tricky part. So then actually, for many years, there were several papers about different sets of properties. People were studying bipartiteness, K-coloring, I don't know, some set, some cuts, and I don't know, K-connectivity. And then actually, there was a fantastic general result, which was shown by Alon and Shapira in a sequence of papers. That they show that every hereditary property can be tested in constant time, even with one-sided error. Now, what is the definition of hereditary property? I'm mixing this up with monotone properties, that you can remove edges and vertices. Sorry?
It's usually minor.
Oh, yeah. So that you can do any contraction and remove any edges. Yes.
Isn't it every subset induced subgraph?
Yes. Yes.
I don't think you can take minors.
Yeah.
I don't think you should take contractions.
Yeah.
Minor.
Okay.
Closed under vertex division.
Close on the vertex addition.
Deletion.
Sorry, deletion. Yes. Okay. So planarity is, for example, hereditary. So I do remember that many, many years ago, there was a fantastic paper by, Bela Bolobash was studying hereditary properties, and his first sentence was, every interesting property is hereditary. It's not true, but to some extent, most of interesting properties are hereditary.
Other than graph isomorphism?
Sorry?
Other than graph isomorphism?
There are some more,
Yeah.
but very few. So essentially everything, no, not everything, many things can be tested in a constant number of rounds, which is a fantastic result.
Sorry, Artur, what was the graph isomorphism? What is the property?
It's not hereditary.
No, but what is the property?
Oh, so there are two ways of phrasing it, usually. You can be given two graphs and asked if they're close to isomorphic. But I think more in fitting with this scenario, there might be some fixed graph, and now you're given a new input graph and you're asked if it's isomorphic to the fixed graph.
So, okay, even actually have the definition. I mean, I was trying to check you whether you are familiar with these notions.
Sorry, Arthur, can I ask a question about just the previous slide where you said that for bipartiteness, you get this 1 over epsilon squared. Is it known whether there are little over 1 over epsilon squared algorithms if you want to do something more clever?
I will comment on that soon. So that's a fantastic result, a very general result. And really, for the first few years when people were studying graph properties, they were studying all these specific properties, and they would say, oh, here we have complex 1 over epsilon to 5, here we have 1 over epsilon to 20, here we have exponential, whatever. And here, this is a general result, which is a fantastic thing. It's a fantastic characterization. I remember that, so actually they prove it in several papers. I mean, my first impression was, okay, so this field is gone. We know everything here. There are some problems, but, so this is really the main lemma what they were showing. The main lemma was, if graph is epsilon far from satisfying a hereditary property, then with high probability, there is random graph of this size, which is some function of the property and epsilon, doesn't satisfy P. So essentially, you are given a big graph, you are randomly sampling, and you are saying, if graph is epsilon far, then you will find a counterexample. Okay, so that's a fantastic result. And the idea here is to use some actually extension of Semredi lemma. And can be extended to hypergraphs, which was also actually a very nice thing. Now, this is really a complete characterization if we are happy with algorithms with one-sided error and we are interested in complexity which is constant, just a function of epsilon. There was an extension to two-sided error testing, and informally it's slightly more complicated, but this is something like with two-sided error, a graph property is testable, which means we can do it in constant time if we can reduce testing to a finitely many Semredi partitions, whatever it is. And this was done by Alon, Fisher, Newman, Shapiro a few years later. Okay, so that's fantastic. So my interpretation of that is that we have very fast property testing. Most of things can be tested in constant number of rounds. They're all very simple, so algorithmically nothing interesting. The analysis is often very hard in the sense that we have this Semredi lemma, which in principle nowadays may be standard, but it's still a non-trivial tool. And this is really done by the fact that we can abstract from algorithmic part. We can essentially only focus on the task of some combinatorial arguments. Now, one problem with this approach is that traditionally, the running time is very slow. So the running time is 2 and many 2's, 1 over epsilon in the exponent. And this is something which is actually inherent in the approach. There is a lower bound which is showing that if you want to use this approach, you cannot do better. So this is what is a tower of 2. So you write C many times 2's. And for example, tower of 1 over epsilon. When epsilon is equal to half, which is very poor approximation, is you have to write 65,000 many times 2. So this is something which is disappointing. But it's constant. And to some extent, we do know that for many problems, we do know that for some problems, you cannot really hope to do anything better. Still, sometimes the running time is much better. And people have been trying to see what is really the complexity. Whether it is 1 over epsilon square, maybe 1 over 2 to 1 minus epsilon, etc. So this thing for being triangle-free, this is something which is known as triangle removal lemma. People have been studying this in details, and currently the best bound is actually not a tower. It's only not a tower of 1 over epsilon. It's more like tower of log of 1 over epsilon. So triangle removal lemma, or actually checking how difficult it is to test if a graph is triangle-free, we do not have any lower bound. I mean, maybe trivial polynomial lower bound of 1 over epsilon. But the state of the art is really of this sort. And the main reason why, so this is by Jacob Fox, he actually obtained this using something like, he was able to abstract Semredi lemma and got this bound using some slightly different arguments. So this is kind of the setting, and I wanted to come back to the question also that Sesh asked. So an exciting open question in this field is actually, what is the complexity of testing bipartiteness? So if you want to just use this algorithm, and I also actually wanted to point out this reduction, that these are all the algorithms that want to study. Sometimes it's not really the case. So these are all the algorithms if you are happy with quadratic laws. But sometimes you are not happy with quadratic laws, and you would like to really understand what is the complexity of testing bipartiteness. You have given a graph, and it's not enough just to sample some vertices, but you just want to sample edges. And I think that still a great open question is what is the complexity of testing bipartiteness? Because of this result, is we know that we can do it in time 1 over epsilon square. And there is also a lower bound, which is epsilon to epsilon to minus 3/2. And I don't think that there is anything between. Am I right? Yes.
No, that was not triangle freeness. I think there is a lower bound that says we need super polynomial.
Okay, so maybe super polynomial. But what I'm saying is,
oh yeah,
I mean, so the main question, by the way, this is a fantastic open question. So this paper was in the Annals of Mathematics. These are people are really excited about triangle freeness. What can you really do for triangle freeness? The property sounds trivial, but it is not. Okay, so here, I mean, this is one of most interesting questions in property testing for this adjacency matrix model, which is also actually often called dense model. Any questions about this?
Yes. Do you remember the reference for the lower bound?
Trevisan and Bogdanovich. Was it Bogdanovich? Was it Bogdanovich? No, I don't remember what was his name.
Bogdanov and Travis.
Maybe Bogdanov. Okay, I don't. Yes. And actually, they do have complexity epsilon to minus 2 minus some small constant, assuming some conjecture is true. So conditional algorithm. And answering maybe such question, I think we do know that we have to sample at least 1 over epsilon vertices. So this one I think we do know. So the thing with triangles, that complexity is 0, it's unique. There are very few things which usually 1 over epsilon is a trivial lower bound for almost everything. Okay, so now there are some problems, some challenges. Why kind of adjacency matrix model or dense graph model is not always great is, first of all, constant time is usually depending on this 1 over epsilon, and this might be very high dependency. Secondly, the distance is epsilon's n square, which is really quite significant. So people have been trying to think, okay, what can we do about other models? So I think the most natural model, actually, if we're studying graph algorithms, sometimes we do pay attention to adjacency matrix, but usually we're interested in adjacency list representation. So what does it mean? It's a given graph, 5 vertices, and here we have all the neighbors on the list. So people have been studying this model, and here we are saying, well, epsilon far away if we have to modify at least epsilon fraction of this adjacency list to obtain a graph which satisfies given properties. This means we are allowed to modify epsilon times m edges, add or delete from the graph. And here the oracle that people have been studying is, okay, give me the ith neighbor of the jth vertex. So this is kind of constant time access to the input representation. So when the model has been introduced, I think this was by Goldreich and Ron, the first model that they have been studying is the model of maximum degree D. So this actually, so maybe you can think why people study that model. I remember that Oded Goldreich was saying that kind of it's a very natural function representation. You are given a graph which is just function from, n times d inputs, and you are given 0, 1 answer. So here we are saying that where epsilon far means we have to modify at least epsilon dn edges to obtain a graph satisfying given property. And this model, unlike the previous one, is not just relying on combinatorics, but it's having lots of algorithmic techniques. So random sampling, but then we have local search, random walks, this kind of much more interesting approaches that people have been using in order to study some properties. Okay, so first thing about connectivity. So this kind of a basic thing which people have been asking maybe as the first question, how to test whether a graph is connected. So what does it mean that a graph with maximum degree d is at epsilon far from being connected? If you look at this, it means it must have at least so many connected components. And it looks like that's enough to obtain a constant time algorithm. Actually, one needs to do slightly more. We want to have that we have many small connected components. And this can be easily obtained that we have at least epsilon dn half connected components of size at most 2 divided by epsilon d. Yes. Once you have this property, you can come up with a very simple algorithm. What the algorithm is doing, you randomly sample some number of vertices, and then what you are doing, you just want to check whether your connected component is small. Yes, so what does it mean? If you know that all connected, that there are many small connected components, if you randomly sample enough many vertices, you know that you will hit some vertex from that connected component, and then you just run BFS. Graph is bounded degree, so you can easily obtain a connect. You can easily check whether a given graph, given a connected component is of size at most there. And that's the entire algorithm. So somehow very simple analysis. Does it make sense? You have many small connected components. You know one random vertex will hit one of those if you are epsilon far, so you will find it. So testing connectivity can be done in such a way. Now, this actually can be extended to testing H-freeness, for example, triangle freeness. So graph is epsilon far from triangle free if we have essentially n over epsilon disjoint triangles, and then if we are randomly sampling some number of vertices, we'll be able to hit one. In general, people have been asking the question, which properties can be tested in constant number of time, a constant time. We would like to obtain characterization. We don't have it yet. Let me actually, so here our goal is really to check constant time. And actually people observe that unlike in the dense graph model, in this model, many properties cannot be tested in constant number of rounds. So bipartiteness is one of these models. So Goldreich and Ronde actually show that we can test bipartiteness in time sample like root of n. And the algorithm is quite simple. You sample 1 over epsilon vertices, and then you are running lots of random walks of polylogarithmic length. And then you are looking at the graph induced by these random walks. And the point is that if any of the starting vertices lies on an odd length cycle, then you know that the graph is not bipartite. And you will just reject such a graph. The point is that you are running lots of random walks, and if the graph is epsilon, so some like root of n random walks, if the graph is epsilon far away from being bipartite, then many of these random walks will be coming together, and then you will see many long cycles, and you will be able to check whether the graph is bipartite. The analysis is really relying on this fact that if graph is epsilon far from bipartite, then there are many polylogarithmic long random walks cycles of logarithmic length. So the whole algorithm is kind of relying on that part. Now, the analysis of this fact is quite elaborate. I remember first time I have seen it, I thought, wow, it was maybe very long proof. Nowadays, maybe we are more flexible with understanding this type of thing. The idea was first to study if the graph is kind of a good expander, and then we know a lot about random walks. And then if the graph is not a good expander, then we have some small cuts, and they were able to put things together to obtain the analysis. Analysis still, is there any proof shorter than 20 pages? So it's complex. I mean, I remember that if I were giving this talk 10 years ago, I would write very elaborate. Nowadays, we have seen more complicated things, so it's only elaborate. And actually, they also show that it cannot be done better. So you need root of n time to distinguish between just two classes of graphs. One is, you take Hamiltonian cycle, and then in one class of graphs, you add a perfect matching. In another, you add a perfect matching so that all cycles are of even length. And the complexity of distinguish between this case and that case is root of n. This is shorter, the proof of that. So the main message should be actually, I wanted to show you bipartiteness is a very nice property. The main message is we don't have constant time algorithms for some basic properties like bipartiteness. Then actually, there was a paper by Bogdanov, Obata, Trevisan, who showed that if you want to check three-colorability, the complexity is essentially linear. So you essentially have to check all the edges in the graph in order to test three-colorability. Then I thought actually that this is maybe one of the nicest problems around. So testing planarity. We want to check if a graph is planar. So testing planarity, in the first instance, I thought it's quite hopeless because there are some graphs which have actual logarithmic girth. And in these graphs, if you are looking at any constant number of vertices, this graph is planar. This somehow suggests that, and actually they are very far away from being planar because these are expanders. So there are some expanders where the girth is logarithmic and so they are very far away from being planar, but locally they look like planar. So somehow the feeling was this should mean that maybe no constant time algorithms are possible. And then there was a very nice paper by Benjamin, Shram, Shapira, where they show that actually testing planarity can be done with constant number of queries, with two-sided error. And my interpretation of this algorithm, which is maybe different than of some other people, is that what you are really doing is you are randomly sampling some number of vertices, you are looking at the graph around these vertices, and you are looking at the shape of this graph. And if the shape is appropriate, whatever it means, you are saying this is planar. If the shape is not appropriate, if some graphs are happening more frequently than others, you are saying this graph is non-planar. I thought that this was a very cute thing. And the only problem was actually that the runtime was not great. So the complexity was 2 to 2 to 2 to poly of 1 over epsilon. And then there was slightly other algorithm by Hasidim, Kellner, Nguyen, and Onak, who improved the running time to 2 poly of 1 over epsilon. The algorithm was maybe simpler. The analysis was definitely simpler. The idea was that if graph is epsilon far from being planar, then either it has lots of constant size non-planar subgraphs, or has lots of small subgraphs which don't have good separator. If you don't have good separator, you know the graph is not planar. Then there was a very nice paper by Levy and Ron who improved the complexity to 2 log square of 1 over epsilon. And for some time, it was a fantastic open question. Can we actually obtain complexity which is polynomial in 1 over epsilon? And this is what Kumar, Seshadri, and Stallman did. They showed that actually we can do it in time, which is polynomial in d divided by epsilon. So planarity can be tested in constant number of rounds. And there were some nice consequences. I mean, it's not only for planar graphs, one can actually extend it. And heat analysis. Any questions?
So D cannot be average degree. It's
No, it's maximum degree. Yes, it's maximum degree. So these are graphs of bounded degree, and D is assumed to be constant. So there are some extensions to minor closed families, etc. This algorithm was really doing some very nice study of some random walks. Then actually there was very interesting question, what about two-sided error? So what does it mean? The feature of all these algorithms was that we're kind of looking at some statistics, and if some statistics are telling us, okay, most likely this graph is planar, we're accepting. If it is not, we're rejecting it. But we can easily reject planar graphs. And great thing about one-sided error is that we would like to kind of have algorithm which, if the graph is non-planar, we have some proof it's non-planar. So it's actually, one can show that we cannot do it in time better than root of n. And then a few years ago, there was again paper by Kumar, Seshadri, and Stallman, who showed that in something like root of n complexity, we can check whether the graph is planar with one-sided error. So these were very nice results.
Sorry, I'm stuck in the previous slide. So the results of Levy and Ron, is it d to the log squared of 1 over epsilon, or
I don't remember what
It's d to the log squared d over epsilon.
so generally d is not, I mean, we cannot assume it to be constant for general planar.
Yes. Oh, yes. So this is only for bounded degree graphs. Yes. So general graphs, this one, unless Sash has some other idea. So, and one can usually extend it to some, minor closed properties and graphs. Okay, I see that I'm actually slower than I expected. So people have been actually also studying expanders. I'm assuming you do know what expanders are. The idea was that kind of expanders is something which is opposite to planar graphs. So planar graphs don't mix fast, and expanders mix fast. So people were thinking, okay, what is the complexity there? And then there was a paper that actually testing expansion, one can do it in time, something like, again, root of n. And that's also needed. And here's kind of a typical algorithm. And I'm sorry for speeding up. I still want to talk about models, which are exciting. So this is an algorithm. And so one can actually extend testing expansion also to testing some clustering properties. So if we want to say, okay, graph has some number of clusters which behave like expanders, we can test this type of properties quickly in time root of n. Yes.
Is that for
Bounded degrees.
bounded degree? It doesn't have to be the same degree. It doesn't have to be that everyone has the same degree.
Okay, so actually testing expansion, one can actually extend this result. For testing expansion, I think that one can extend at least some of this result to general graphs. But I'm not sure. I think Pan did something.
Yeah, I think so.
Yeah.
Pan and Peng have something.
Yes. Yes. Okay, I still want to talk about planar graphs. So my goal is really to give you an overview, what has been happening in this field, what are also interesting views, what are interesting models for testing in graphs. So there have been also some papers about testing in planar graphs. So far we have been assuming our input graph is arbitrary. but bounded degree. Adjacency list representation, bounded degree. So what is if the input graph is planar? So we have shown that actually testing bipartiteness in such graphs can be done in a constant number of rounds, in constant time. And the idea was quite simple: pick some constant number of random vertices, run random walks, explore its neighborhood. If graph is epsilon far from being bipartite, then we'll be able to spot something which is not bipartite. And this was the complexity we obtained. But this was kind of the first step. Shortly after, there was a very nice characterization where Newman and Zoller, they actually showed that testing any property in hyperfinite families of graphs of bounded degree can be done in constant number of rounds in two-sided error model. Now, what is hyperfinite? It's something more than planar graphs. These are graphs where we kind of, I think, if I look in the ball of size D, you will see, of size K, you will see something like, you will kind of just see some small number of endpoints. So that's something which planar graphs they have. And this must be true for any ball. Essentially, this means that, this is non-expanding, which means that you cannot just expand exponentially. Now, I want to move to the next model, which I actually think is maybe the nicest, because this is the model that people are traditionally studying. If you are given a graph, the graph is given as adjacency list. You don't care about the degree. So here we are saying a graph is epsilon far away if we need to modify at least epsilon fraction of entries in adjacency list to obtain a graph satisfying P, and this means epsilon fraction of edges. And here we don't make an assumption for maximum degree. This model required some assumption about the oracle model, oracle access. So what we are assuming that you are given, so you can randomly sample a vertex, and then you can randomly sample a neighbor of that vertex. It's kind of the most natural model. Otherwise, you could also actually assume that you can ask about the degree of the vertex, and then you can ask about the ith neighbor of that vertex. Most of the techniques which we have seen so far, they don't work in this setting. For example, testing planarity, which can be done in the previous model in constant number of rounds, here requires n squared time, root of n time, even in two-sided error model. And the reason is, think about the following thing. You are given an empty graph on n nodes, and you are given a clique of n nodes, and then isolated n minus root of n vertices. You will never hit any edge in this. So you need to perform at least root of n queries to the vertices in order to find an edge. So kind of you need root of n edge. You need root of n time. So in this model, kind of the situation is much more complicated. Testing neighborhood is just expensive. Graph exploration is expensive. Yeah.
Why would you not have a single edge out instead of root n? Because your definition seems to be epsilon times e, not.
Okay, so you can add some extra vertices here, edges here.
I'm saying why the lower one is not omega n, because you just have a single.
Oh, okay, because this graph you don't have a single.
Just pick a constant size non-planar graph and make everything else isolated. So, and then it takes you omega n queries to each one of that thing.
I think you should assume that
already very far from with your definition of farness.
you should assume graph is connected, otherwise things break down. So assume there's just one connected component. And then you could put an empty graph, you could make it a cycle and then a cycle with a clique and one edge between.
Or you could assume that the number of edges is linear. In the number of vertices.
Otherwise you could just have isolated vertices and then it's boring.
So this is really very much, yeah, so people have been studying triangle freeness, then bipartiteness. They show, for example, this lower bound, which is quite weak. We have been studying this setting for arbitrary planar graphs. So we couldn't do anything for general graphs. So expansion is one of these properties. Why expansion actually is possible to do in general graphs? Because you can reduce this to bounded degrees to a large extent. So if you have some property that you can reduce it in some nice way to bounded degree graphs, you are in a great shape. But in general, you cannot do that. So we have been studying testing in arbitrary planar graphs. With Mone, Mizahadet, Onak, and Zoller, we came up with an algorithm showing that testing bipartiteness in such graphs, planar graphs, can be done in constant time. And the idea was really how to explore neighborhood of a node quickly. So the algorithm was essentially as follows: run many short random walks, and we're saying that if a graph is planar and epsilon far from being bipartite, then we'll find an odd length cycle in that way. And this odd length cycle will be of constant actually size. So, yes. So what we really show, we reduce everything to checking CK freeness, where CK is a cycle of length k for even k, where k was of order 1 over epsilon. And then we're just testing that. And I see I have less and less time. So actually, we have been able to extend that. So we're able actually to show that testing H freeness in general planar graphs can be done in constant time with one-sided error. When H freeness, H is any finite graph H. And then actually we're able to show that this is a characterization. So any property which is testable in constant time, can be reduced to testing H freeness. So this was a nice thing because it was characterization. And actually later people show that one can slightly extend it to some monotone or minor closed properties. Okay, I'm running out of time. So I still wanted to tell you about one fantastic model, which is directed graphs. So the model has been introduced by Ben and Ron. And they were studying model of directed graphs with bounded minimum and maximum degrees. Sorry, with bounded maximum in degrees and bounded max out degrees. And what I want to say is that this is an interesting thing because there are two main models. And one is easy, which is bidirectional model, which means you can access edges in both directions. And then actually, if you think about it, this is something which is very similar to undirected graphs. You are at a given vertex, you can go to using outgoing edges and also incoming edges. And then it's very similar to undirected graphs. However, if you have one directional access model, then this is something which is completely different. And this is something which is very challenging. In this case, very little is known. So think about that. Is a graph weakly connected? You know, it's something which can be easily checked, which means this is this bidirectional model. It's just connectivity in general graphs. However, if you want to check if graph is strongly connected, this is something which is very complicated. And I think there is some, I don't know what is the upper bound here. And to 2/3, maybe root of n, it's kind of not much known about it. A few years ago, we had actually some nice paper with Peng, Zoller, and then Wang, where we're showing that this bidirectional model, we can, with very weak conditions, we can connect to one directional model by showing that if something can be tested in constant query time in bidirectional model, then in sublinear time, we can test it also in the other model. But the sublinear is essentially n to 1 minus epsilon. Okay. So many graph properties can be tested efficiently. That's what you have seen. Sometimes constant, sometimes not, but our understanding for some models is very patchy. We still do struggle with understanding, especially general graphs or directed graphs. And the tools, I think actually the fantastic thing here was, I have seen many great tools developed to study these graphs properties. Let me actually also very briefly mention thing I have not mentioned, or I'm not going to mention, almost. Tolerant testing is another model which people have been studying. It's essentially the problem that I want to accept graphs which are either satisfying property or are epsilon prime close to satisfying the property. But if this is more than epsilon prime, I want to reject, I don't want to accept. So there have been some work, the model has been introduced, Parnas, Ron and Rubinfeld, and this kind of related to distance approximation. And the last slides are really about very much topic of this workshop. I mean, what I have noticed is that for many problems, we were able to leverage of existing property testing tools to obtain some very interesting algorithms for optimization problems. For example, there was this fantastic algorithm for estimating the weight of MST in bounded degree graphs, so that you can come up with 1 plus epsilon approximation in time which, for bounded degree graphs, when weights are small, is essentially constant. I thought it's a very nice result. And then there have been many other works on that line. I think that this is something which yes. Thank you.
It's about the Dunn's graph model. So you mentioned that algorithmically it's kind of not interesting because, you know, the canonical tester will tell you like, just stay quadratic speed up at blow up at most. This is assuming you want constant, right? If you are willing to say I'm okay with paying like a square root independence or like a polylog independence.
So let me rephrase it. If we don't care about the quadratic speed up or slowdown, then all the algorithms, almost all the algorithms that are worthy considering, you can always rely on this. If you're interested in exact bounds, then you can try to do something better.
Not even just the exact bound, right?
There is no claim about constant time algorithms. It's for any T. If you have an algorithm require T queries to adjacency matrix, you can essentially always, but essentially, reduce it to algorithm which is checking root of T, which is checking T vertices at random, and then it's looking at the graph induced by those. So that's true for root of n time algorithm, etc. Yes.
I have 3 very, very general questions. One, people looked at this whole testing with predictions, that the predictions might be faulty.
I do not think so.
As a whole new thing, okay, and
or maybe there was some. I don't remember.
In the context of distribution testing, in the context of distribution testing, then people have looked at in the context of distribution testing, it has been looked at.
You try to test if an input is coming from a distribution.
You get samples of a distribution, and you would like to distinguish whether the distribution, the underlying distribution, has a certain property. Okay. So that's one example. And also counting motifs in graphs, like the number of 4 cycles in certain settings, like streaming settings, with advice. That's something I know about. I'm sure there are other things.
I think there were papers about fault tolerance or something of that sort.
Second one is, so to what extent are predictions explainable? if you wanted to you get a prediction, it says it's likely to be this or not. Is there some way that, that some notion of, can that be augmented with some notion of why, of the explainability of the result?
I don't know.
My final general question is, I guess it's the usual, to what extent is it impacting applications, say in ML, in machine learning, in testing of large social networks?
So I think that some of the results here, okay, one of the last slides was really about impact on algorithms.
Yeah.
And I think that most likely the impact is not direct. The testing algorithm, okay, I remember that Sesh, his paper about planarity testing, it's actually had some impact on finding some features of ML graphs or some certificates that the graph is not planar. But often this is more like the techniques can be later used for some algorithmic problems. Now, I can imagine that some questions related to testing some clusterings could have some impact for some algorithms using a method. So this one, I don't know.
And I guess some of these, what you're saying is that some of the techniques that have been developed within this field have become results in combinatorics.
I mean, so this is maybe easy because actually this algorithm about dense properties, this was a very nice result in combinatorics. They kind of had some extension of Semerelli lemma, some strength.
So, yeah.
So, and I actually think that in sparse graph model, some tools used to study random graphs, random walks, is actually something which again can have some impact on. Maybe it's actually taking use.
Is it bad if I try to add a couple? I just want to add a couple of examples to whatever. So first of all, I think you should come to Sesh's talk in the afternoon because he always has impact. The other thing I wanted to say is there was a paper by Tal Wagner in a few years ago in which he, through the lens of property testing and sublinear algorithms, he looked at algorithms that estimate something. It's essentially it's diameter, but diameter starting at every so it's essentially the radius. So you're given a graph, and you would like to know for each node u what is the farthest node from it. So it's sort of like the radius if you center at u. Okay, so this is something that people in practice seem to want to compute. And he looked at typical algorithms that people use, and he analyzed them through the lens of property testing. So he, for example, used the algorithm, using the analysis of Parnas and Ron, he gave better analyses of these algorithms that were used in practice. And then using another streaming algorithm that has, I think Sepide, and I don't remember who else is on that paper, but the people in this room were on that paper. And he used that to show a different algorithm that was to analyze and give a better analysis of a different algorithm that was used for the same problem. So these ideas do have something to say about algorithms that are already used in practice.
And I think that this is actually a great topic for this semester, to try to understand if there are any real applications, or maybe people would be able to come up with some new applications.
That's a good question. So actually not about real applications, but theory applications. So in algorithmic problems, do we know instances where property testing shows up? And I particularly want to understand how the epsilon fourness shows up. Like, do we have other algorithmic problems where the epsilon fourness is somehow implicit in the problem? I mean, I don't know. Maybe if the instance is epsilon 4, we can make some algorithm faster, and we first test for whether it's 4 or not, and then we change the algorithm. The algorithm takes a different route as a result. Are there applications of this kind?
I would think so, but I don't remember. So I remember that there were some papers about, was it oblivious testers or no? Parametric, no. Essentially that, okay, I don't remember.
I mean, some of these hyperfiniteness things you're talking about are sort of like learning. You can like learn a signature of the graph, and that's the fundamental technique that's used. So.
There are also instances where the techniques vary all over the place. So I remember work by Settler and others on the regularity-based techniques. Also, what is the spirit on that?
I guess I can completely understand that the technique finds a different application. I'm trying to understand how epsilon fourness shows up itself as a concept in algorithm problems.
One example is in graph coloring, for instance. In delta plus one coloring, if your graph is epsilon far from having cliques, you know algorithms which are much simpler. But it should be epsilon far from having delta cliques, not epsilon far from the entire thing being it. You know, and all this graph decomposition that we do, they are really based on trying to find this decomposition into almost cliques and things like that. They are based on a probability testing idea that you're either having a clique or you're having a sparse graph, and a sparse graph so you can handle easily. So one application will be if you can test quickly that your graph doesn't have those cliques, you don't even have to run the complicated problem.
Any other questions?
So I've got another question about the first part of the talk. And so there is that notion of POT, proximity of the use tester. Is there a character which basically asks, like, I just want to do local tests and repeat them until I can reject? Is there any characterization of what is testable, even in the dense graph model, for POTs?
I don't know. I think I don't know whether there is anything general.
Okay, thank you, Artur. And I think we're going to take a little bit more than 5 minutes left on the break. So, so sorry, I didn't check the clock. I went crazy. But, the questions were great. Thank you. So maybe we'll start in 10 minutes. It's the 15 minutes.